Okay, so previously we learned a few things about complex integration. Oh, that's a part that I don't like. I'm sort of a blue person. I like blue colors. So when Fz is analytic inside of C, Fz is analytic inside C, then what do we have? The Cauchy's integral theorem says this is going to be 0, right? Number one, there's Cauchy's integral theorem. If there's a point Z, if Z is inside, and of course Fz is analytic, then we have two pi I Fz naught. It has another name called Cauchy's integral formula. And thirdly, if Fz can be considered as a Laurent series, P minus M, P0 plus P1 etc. And of course, Z naught is the same. Z naught is inside of C. Then, obviously, it's 2 pi I B minus 1, right? So when Fz is written, expressed by, this is called Laurent series. Then if Fz can be very complicated and expressed by this series, then if you do integrate, then it's just 2 pi I B minus 1, right? So this is called residue. And sometimes written as residue Fz naught. So that's what we have been learning for the past week. So today we are going to do a further analysis of residue and how to find B minus 1, that coefficient, and then do some simple calculations for some integrals. And we might finish a little early today. I have an appointment to some meeting. So maybe if it is okay with you, I'm going to finish around, maybe a little around after 4. So maybe half an hour, a little bit earlier than the usual. I can be late at the meeting, so it's no problem if you don't like it, you can continue. Like it. Okay, so the residue. Our business is residue. If Z naught is not finite, but if we multiply Z by Z naught that become finite, then we say Z naught is a singularity is called singularity, and pole of order 1 or just simply simple pole. So whenever Fz is not finite at some particular point, that point is called singularity. The singularity can be classified in many different ways. So it's called singularity. For example, when Fz 2 so obviously when Z is equal to 2, what happens? Denominator, this is called the denominator. So when Z is equal to, when Z approaches 2, what happens? Fz become infinite, right? So actually, it can be either plus minus infinite. So when Z is 2 plus epsilon, then it's negative infinity. And when Z is 2 minus infinity, it's negative infinity, positive infinity, right? So even if it is approaching infinite, it is a very extreme range from minus infinity to infinity. But anyway, so it's a singularity. However, we can check. This is when you multiply Z minus 2, what happens? Finite, right? It's simply 1. It's finite. So Z equal 2 is a simple pole. And obviously residue is 1. When Fz, we can continue some more examples. Z minus 1, Z minus 2. So how many singularities do we have now? 2, right? We have 2 singularities. 2 singularities at Z equal to 1 and Z equal to 2. So we can check whether this is a simple pole or double or higher order poles. So Fz, simply Z minus FC becomes -1, right? And Z approaches 2, Z minus 2, FC is 1, obviously finite. So they are simple poles. So Z equal to 1, 2 are simple poles. A bit more difficult case is sin Z. So singularities, you can at least know the where is the singularity. That's where the denominator is 0, right? The singularity is at Z equal to. There are many singularities in this case. Obviously, 0 is 1 point, right? 0 or plus minus pi, plus minus 2 pi, etc. So it has many singularities. And so let's try to check one of the singularities, Z times FC. Actually, I think you learned this special limit in high school called L'Hopital's rule, right? So this is 1. This process is called L'Hopital's theorem. You probably have this memorized in high school, right? So L'Hopital theorem says it's a French name, L'Hopital. If GZ and FC goes to 0, as Z becomes, no, okay, sorry, I'm going to write it in the real analysis. X, and this L'Hopital theorem you probably have memorized in high school. But actually can be proven very simple way in 2 lines. So let x is x plus delta, then can be rewritten as delta goes to 0, fx0 plus delta, gx0 plus delta, right? I haven't done anything. So this is obvious, right? I mean, we know that when the condition in the problem says gx0 is 0 and fx0 is 0, so we are going to take a limit to find the limit. So limit, we can, if x is a little bit small variation from x naught, then this limit x approaching x0, fx over gx can be rewritten as delta goes to 0, fx0 plus delta, gx0 plus delta, right? And I told you that in mathematics, especially in complicated form of mathematics, you can do nothing. So you can either subtract to add 0, or divide by 1, or multiply by 1. It's the same thing, whatever you like to do. So what you can do is actually subtract this x0, because this is 0, right? You haven't changed anything. And you subtract gx0, which is again 0, right? So you have x0 plus delta minus, you can subtract 0 anytime. And denominator also you subtract 0. And it's about time to delta. You divide by delta and multiply by delta. It's the same, right? But however, this part becomes what? When delta goes to 0, this becomes derivative. So this becomes f prime x0. And this becomes g prime x0. Right? So L'Hopital's rule says, I can continue to the next page, I guess. So, fx. Yes. Continue. So, as a result, fx0, then limit fx was actually. So let's just be consistent. Fx gx same as gx prime fx prime g prime x0 f prime x0. And some cases, this L'Hopital's rule can be used very wisely. For example, if an fc is of nz over dz and has a simple pole at c0, then residue of c0 simply so proof is actually easy. So so dz, the denominator, this, right? nz plus n prime z. So the limit z simply nz now. So that's the denominator. Denominator, prime of the denominator is this. And if we take a limit to z approaching z, this goes to 0, so only ng survives. So this is the residue. So this property is very useful, so I'm going to use it many times. And probably, maybe 80% of the cases is the simple pole. But nevertheless, it's going to be useful to I'll give you a chance to copy. Am I going a little too fast? Yes or no? Okay. Okay. So when f general case, f and so and continue. But finite. Then C0 is a pole of order m. And in this case, the residue can be found by this way. And take the limit. I'm going to solve it. So m minus 1 factorial dzt m minus 1 z minus z star m fc. had to have this last time, right? So, as an example, okay, I'll let you copy. For example, let's consider this fz z squared z plus 2 . So how many singularities do we have in this case? Singularities at z equal to 2, 0, and z equal to minus 2, right? So singularities at z equal to minus 2 and z equal to 0. So z equal to minus 2 is obviously simple pole, right? So we can check. Minus 2 z plus 2 fz is basically z goes to minus 2, z squared 1 is 1 over 4. So it's a simple pole, right? And that's your residue. And residue f minus 2 is 1 over 4. However, ZFC still infinite, right? So on the other hand, it's finite. So FC has a pole of order 2 at z equal to 0. But what about the residue? Residue? You need to differentiate. So the residue of f at z is limit to 0 approaches 0 dz d z squared fz. So this limit to z goes to 0, 1 over z plus 2 is minus z plus 2 squared is minus 1 over 4. So that's your residue. So obviously in the next quiz, I'm going to ask you to find the poles and classify the poles and find the residue, right? I have done some cases because I'm showing some examples. So I'll give you the following homeworks. Okay, you still need to copy. So everything is straightforward, right? Not very difficult. So in order to prepare for your next quiz, I'm going to ask you the following still popping, right? So here is quiz. Oh, maybe somebody following homework. Homework. Design your own problem. Simple pole. And residue. Pole of order 2 and residue. Pole of order 3 and find residue. Find. You need to find, calculate. 5 each. 5 each. 5 each. So design your own FFC. Whatever you like, that's okay, right? So maybe you can solve 15 of those problems. You can solve basically any problems. So one possible exception, surprise is this function. Does it have a pole or not? Singularities. No. In real case, exponential x is never negative. However, in complex case, when z equals what pi I, what happens? Exponential pi I minus 1, 3 pi I minus 1, 5 pi I minus 1. So is minus pi I minus 3 pi I. So it does have infinite singularities on the imaginary axis, pi I minus pi I, 3 pi I minus pi I. So it's odd numbers of pi I. Even and odd, you know, right? Even is a jaksu, odd is holsu. So even pi I has singularities. So let's try to classify this so try z to pi I, z minus pi I, 1 over exponential z plus 1. You can apply the L'Hopital's rule. So it turns out that exponential pi I, right? It's minus 1. That's your residue. So in theory, you can calculate any residue if it does have a singularities, right? So I'm going to state the one final theorem. If there are singularities of Fc inside of C at C0, C1, Zn with residue F0, residue FCN, then the integration of this function is simply the sum over residue FCK. And this is called residue theorem. Again, Cauchy's residue theorem, or Cauchy's residue theorem. Sometimes it's called calculus. So this is, I'm just going to state without proof. Actually, I have done many cases already. So if we have a very complicated function, then, and if you are asked to integrate, then the only thing you need to find is just find the residue, and then sum over it, then you find the solution, integral. So that's actually very powerful tool for the mathematicians and engineers and scientists 200 years ago. They didn't have a computer, but they have very powerful mathematical tools that allows them to calculate very complicated integrals, and I'm going to show you soon. So the only thing you need is just a pen and paper, or pencil and paper. So before I proceed, why don't you take a break for 3 minutes and continue. So this is probably the most important part of the complex analysis, and the reason why we are learning that. And these days we have a very powerful computer, so actually probably we don't need that. But still, it's useful. And sometimes even a very powerful computer cannot do exact calculations, but this residue theorem, residue calculus allows to do quite a number of integrals analytically exactly. And Russians, Soviet, didn't have a computer technology until 1990s. So they actually relied on this. Many engineering, solving many engineering problems. And there was one integral table book written by Russian mathematics that contains about 4,000 integrals doing this residue calculus. So I'll take a How do I check? Well, c'est la vie. Oh. So I have been recording in a mute. Oh, let me check if. Okay, thank you. So, what we have just done is we have an original integral. You add simply something 0, which is basically this the round integral CR on the curve, and then make it a complex closed integral. Then you can apply the residue theorem. Becomes 2 pi I residue pi I residue f3 pi I. So we have actually an infinite summation. So let's try to find the residue. This is very simple actually. So residue pi I is equal to z goes to pi I exponential z plus 1 exponential alpha z. And then you can apply that nz over d prime z. So this is basically exponential alpha pi I exponential pi I minus exponential alpha pi I. Exponential alpha pi I. So residue f3 pi I. We can do the same thing. Exponential 3 pi I, exponential alpha 3 pi I is basically minus exponential 3 alpha pi I. So sum over this, sum over minus of exponential alpha pi I, exponential 3 alpha pi I, exponential 5 alpha pi I, infinite summation, right? So let's continue. Still the time. No, okay, it's not mute. So when I said mute for the recording, doesn't that mean that it's not recorded or playback is mute? It's a good question. You can check the YouTube. If it is mute, then it's mute. I think it's mute. So it becomes minus pi I, 3 pi I, 5 pi I, etc., etc. Exponential minus pi I, alpha, 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 right? You have alpha, alpha pi I. So 1 plus exponential 2 alpha pi I plus exponential 4 alpha pi I, etc., etc. So it can be written as minus exponential alpha pi I, 1 plus exponential 2 alpha pi I plus exponential 2 alpha pi I square plus etc., etc. And you learned how to add geometrical series since high school. The geometrical series is a 등비급수. So simply it's 1 minus exponential alpha pi I, 1 minus exponential 2 alpha pi I, right? So it's infinite geometrical series, 무한 등비급수 sum that you probably be familiar since high school days. And you can divide 1 over exponential minus alpha pi I minus exponential alpha pi I. And you can change sign minus minus, it becomes 1 over exponential alpha pi I minus exponential minus alpha pi I. And this is very nice. This is what? 2I times sine alpha pi I, right? That's your residue. So actual integral, I'm going to put some position. So this integral this is a very important part. Alpha has to be less than 1. This condition allows to add 0. Becomes 2 pi I times 1 over 2I sine alpha pi. So this is actually pi over sine alpha pi. Wow. It's really amazing because the original integration has anything to do with the sine or pi. The result seems to be pi divided by sine alpha pi, right? Especially if we said alpha is 1/2, then sine pi over 2 is 1. This is pi, right? So definition of pi, there are many definitions of pi. So pi appears, so I can set alpha 1/2. We have pi exponential x plus 1 exponential x over 2 dx. Previously we have another pi so I'm quite curious why there are so many expressions of pi. Pi is simply the proportional constant for the radius of the circumference. But it must be a very important number because many different expressions give the pi. Right? This is really amazing. You're going to see a lot of different pies. So before I proceed, if you have any questions. So far, we have been doing the complex integration with a single valued function. But now we are getting into really exciting area for the multi-valued function. So let's see, let's do that. But I will let you finish the copying of the equations. Yes? Residue actually has a mathematical meaning, but not physical meaning. So the residue means if you do the whole integration, the part of the series that is not vanishing. I mean, we know that right? So any part of the function which is not vanishing when you do closed contour integration. So that is actually the meaning of the residue. That clarify that you asked a question. So that's a rather easy example. And still, so far, we are concerned with the function that is single valued in complex domain. Of course, all the functions we will consider in the real world is single valued. But consider this function. Another example, I. Okay, square root of x. Let's go on to x. So this function actually comes from the case for the gravitational interactions whenever we have 1 plus x squared in the denominator. And so we attempted, but z1/2 is not single valued, right? So when you say fz is because of the denominator, this function is not single valued. When you cross the real axis, it changes sign. So this function is not single valued. Single valued. And has branch cut. On the positive x-axis. So that is a really big concern for us to apply the so far just simply adding 0. So we have to do some trick. Trick is the following. So for this complex function, we have a branch cut. So what I'm going to suggest is this. C1, CR, C2, 0. And we have a pole. How many poles do we have? Here and here. zone C. So this I may need to use it many times. So I make a copy, edit, add to the clipboard. Okay. So you look like a shark with a tail. So sometimes I put the shark in the curve. So on C1, oh sorry, here, the same point, this is the same point on the x-axis. But above, on C1, simply z equal to x, right? On this point, we have 2 pi I. So this point can be considered as x times exponential 2 pi I. So, simply this, x squared plus 1 square root of x, right? Here. On the other hand, in the below the branch cut, it has x squared plus 1 but minus square root of x. Because of this exponential 2 pi I, when you take a 1/2, then you have additional exponential pi I, so it makes minus, right? So this is this here. So as a result, I may use this space as well. So as a result, on C1 is from 0 to infinite, x squared plus 1 root x dx. On the other hand, C2 is what? C2 is coming from infinite to 0, right? So it's infinite to 0, x squared plus 1, but we have minus root x dx because of the branch, right? This integral is coming from infinite to 0, but on this C2, because the extra factor of exponential 2 pi I, when you take 1/2 of this, you get minus extra sign. So this integral becomes x plus 1 minus. But this minus sign is actually very nice, because this minus sign makes this upper bound and lower bound interchange it to make a 0 to infinity to x squared plus 1 square root of x dx, right? So this is going to be very complicated, so but this in the YouTube is okay because it's sequential. You are going to see the sequential because I put this part in the top, but actually on this, if you replay it, it will appear the last time, the later, than this part. So are you still following me? A bit complicated, but the idea is just adding business, adding zero business, right? So Known that this C1 and C2 turns out to be the same. All right, nice thing is I can add Klibat, this. So I'm going to put this here somewhere. Maybe a little bit smaller. I become very proficient. So this whole integral we have C1 C2 plus CR zero but they are the same, right? We have so it become actually twice of this square plus 1 but we know that this is the other two are going to be 0. So basically this is going to be 0, this is going to be 0. It's very easy to show that. And so I'm going to give it this homework. Check it homework. So you can trust me that these two are 0. Then the answer is 2 pi I residue f exponential I pi over 2 plus residue f exponential I 3 pi over 2, right? So this point is I is exponential I pi over 2. This is exponential I 3 pi over 2. So Fz is simply z squared plus 1 exponential z to the 1/2. So the first residue, so residue f exponential I pi over 2 is simply exponential twice of I pi over 2 and exponential I pi over 4, right? Equals to 1/2, z to the 1/2. So it's nz divided by d prime z. So d prime is 2z, right? So exponential I pi over 4. This is I. So this is 1 over 2I cosine pi over 4 plus I sine pi over 4, which is 2I 1 over square root of 2 plus I 1 over square root of 2. Maybe I can use some space where? Here? Do we have? Where's the other space? I can. Maybe I'll try to. Okay, just remember that. Wonderful. I don't think I have enough space. So I have to go to the next page. Yes, correct. Change this. So actually, this is our integral, right? This twice of this turns out to be 2. So, but let's start with FC. FC z squared plus 1 z to the 1/2. So residue f exponential 3 pi I over 2 is twice of exponential 3 pi I over 2 exponential 3 pi I over 4. So 3 pi I over 2 is minus I. So 2 times minus I cosine 4 3 alpha I sine 3 pi over 4 and all sine tan cosine, right? You also remembered from your high school days. So 3 pi over 4 is in the second quadrant. So cosine is minus. So this is 2 minus I minus 1 over square root of 2 plus I square root of 2. And if I remember correctly, residue f exponential 2 pi I over 2 was 1 over 2I square root of 2 plus I square root of 2, right? Let me just double check. 2I. Should have a good short-term memory, which is good. So if we add them together, what happens? Residue f exponential 2 pi I over 2 plus residue f exponential 3 pi I over 2 is 2I square root of 2 plus I 1 over square root of 2 plus actually minus 2I over minus square root of 2 plus I square root of 2, and this cancels each other, right, because the sign, and this becomes 2I over square root of 2. So let's have a space. I can finish. So twice of this is 2 pi I times this 2 cancels each other. 1 over I square root of 2. Something is so this is square root of 2 pi 2I. Yes. Let me check with my note. Correct. I seems to have okay, right. So here comes the answer. So can I write this here? Okay. So finally we have this square root of x1 plus x squared dx is pi over square root of 2. So there is a third occasion of having pi. So if you multiply square root of 2 to this integral, you obtain pi again. So how many pi integrals do we have? So far we have 3, right? So my guess is there are going to be an infinite number of integrals that gives pi. So that's starting over a little bit more complicated when you have non-singular non-single valued function, multi-valued function. Nevertheless, we can still get the integral. And a bit more complicated form is given by this. Actually, I'm going to the next class, but maybe you can do something as the homework. So we have a logarithmic function in the denominator. So So these two, I like to give a homework. Try. Or you can check the previous lecture note and then maybe you can try. This, the second one is really exciting. Exciting. I can give a hint. So we need to have a very complicated branch. For the second integral, we have 1 minus 1. So this is going to be your branch. So we are adding this integral. Okay, so maybe I'm going to use. So dash is a 0. So that part is really exciting. This actually you can use the same but we have 3 poles. Right, because we have 3 poles. So this is hint. So you can try as homework. So next week, so we are going to do this integrals class. But before that, I suggest you try to do this by yourself at home. So preview. Yes. Not review, preview. So, okay, let's stop today. Any questions? And whether we are going to have a quiz or not during the conversation week, 2 weeks from now, will be decided. decide in next week. So if I can finish this two integral, then we are going to have a quiz. If not, then just class. Yes?
17페이지에서
네. 네?
17페이지에서 혹시 질문하나 더
예. 어디서 드린죠?